Good afternoon. What this shortish video clip is designed to do is to replace the missing bit of the audio recording from topic 5. So if you go to the part of the video that looks at Python functions, you'll see that there's a couple of missing pages. So this is what we're going to do. We're following on treatment of synchronization, and let me explain what this rather scary diagram is showing. Right, what we have in mind are two hardware units, and they could be actually implementing any system that you care to name. This hardware system actually wants Unit A to perform some work on its behalf. So what it does is to send the data on the R bus, which is received by this hardware unit, and then the R unit sends what in effect is a request signal called in, telling A that it's put data on line or bus R. And then afterwards, what's actually going to happen is that this unit here is actually going to busy itself processing all the data it's just received. And after a short period of time, maybe it's actually going to put the results of the computation or the calculation or the communication on the A line, on the output line, the output bus. And only when it's done that, it's going to tell the hardware units on the left that it's finished the job, and it's going to send a logic 1 or a signal to the effect that which is going to be interpreted as an acknowledgement. In other words, the system behaves as follows. This unit sends a request for some action. This unit does the action, and on completion of the required action, it's going to send an A signal, acknowledgement signal, back to this unit, saying all the job's done. So one way we can actually represent all that information in time, so the horizontal axis represents the progression of time, is that at some point the inputs, let me see, the inputs are going to change. So where you get this crossing of levels, the inputs actually, this represents a change in the data on the input bus. So the change has taken place at this point in time. The unit on the left then asserts or changes the request line, the R line, to logic 1, and it keeps the logic 1 signal at 1 for the time being. And when the data bus on out, it starts to change as a result of this unit computing or calculating or processing the data received on the R bus. It's going to output it on the out bus, and the bits of data are going to change. And as before, we represent the changes of the bits as being represented by this X symbol here. So at this point in time, where I'm showing where my cursor is at the moment, the data is ready to be sent to the hardware unit on the left. So what happens at this point? The acknowledgement line, the A line here, changes from 0 to 1. And this actually, as a result of that, this is going to cause more of this hardware unit's data to change on the in bus. Right, I mean, it's going to ask this hardware unit to do more work. So all the data changes, and the fact is that at this point in time, when all the data has changed, the hardware unit on the left is actually going to change the request line from 0 to 1. Sorry, from 1 to 0. From 1 to 0, which now indicates a positive request, right? And that causes, at some point, the data bus represented by out here to change its values. In other words, it's done its computation, it's got the data ready, it's sending this new data back to this hardware unit. And when everything's changed, all the bits have settled, um, the let me see what's happened. Uh, this unit is actually going to uh, change the acknowledged line from 1 to 0, which is in fact telling the R unit that the job's been done. It's an acknowledgement. So that might sound a bit complicated, and I invite you to check out um, the operation of these two units in terms of the information about signals in this diagram. It's not too complicated, I assure you. Right. So does anyone recognize this waveform? No, but you will actually be able to do that at the end of this topic. It's called two-cycle signaling. I mean, in the sense that one unit is actually going to tell the other unit that it wants some action by changing a signal from 0 to 1. And when it's ready for the next cycle, it's going to change that signal, the request signal, from 1 to 0. So the positive features about this signaling scheme is that it's very fast and efficient. But there's a bit of bad news, because you need a bit of a bit of extra logic to detect whether a signal is going from 0 to 1 or 1 to 0. But that's not really any problem. It just needs a bit of extra logic and state information. Have a look at this diagram, and this represents another signaling scheme, which in effect is what is called the full handshake, and I'll explain what a full handshake and its significance in a bit more detail in a few moments. So what happens here is that the hardware unit indicates that it wants the unit on the right hand side to do some action by changing its request line from 0 to 1, and that causes the machine on the right hand side to look at the data on the input bus and work on it and get a result from that data. At this point in time, it's done the job. Therefore, it can actually tell. So this is the right hand side unit can tell the unit on the left that the job's been done by changing the acknowledgement signal from 0 to 1. And as a result of that, the unit on the left eventually will see this rising signal from 0 to 1, and it will drop its request line from 1 to 0 in order to start a cycle all over again. So this scheme's slightly different. Some people would say it's significantly different from the scheme I've just explained above. So this is the only real alternative to two-cycle signaling, and it's called four-cycle signaling, or return to 0, because the signal request, after it's served its purpose in alerting the right-hand unit that it needs something to be done, returns to 0. Look, 1 to 0 here. So the return to 0 character tends to result in a very simple and a very natural circuit implementation. But it does require twice as many signal transitions as the first scheme I told you. So maybe you'd like to have a look at that. And two signaling, unlike the two-cycle signaling, the four-cycle signaling requires signals to make two trips to and from an element from each operation. And it might be well the case that two-cycle signaling will be used for long-distance communications, for example, from chip to chip. So our scale of distance is at the level of chip to chip communications. And what more do I have to say that? So I want you to be able to tell me exactly what a full handshake is. And I think this is sort of related to your current coursework, but we'll evaluate that later on. So a full handshake is an important mechanism for controlling the activities of two independent but cooperating systems. And those systems could be hardware or, in fact, software or wetware. So it's important. So let me give you my explanation of what a full handshake is again. So often device A must request an action to be done by device B. But device B's state and speed are unknown to the device A and vice versa. And therefore, it's important that I somehow guarantee that B sees my request. And it's also important that device A actually sees the acknowledgement sent to me by device B as a result of the work being done on my behalf. So I'm going to give you an alternative diagram to try and help you understand this in a moment. So we need to be certain that the device has recognized the request. So the sequence of events of the full handshake is this. First of all, device A senses that device B is still not acknowledging the previous request. It's not responding. Therefore, the request is continued for as long as necessary. In other words, A extends its hand. I mean, we might be able to describe it like that. So in other words, so for as long as the acknowledgement isn't won, I'm going to stay in this state and output a request signal. As long as it takes, I'm just going to hold up my hand until you see it by sending me an ACK equals 1 signal, and then I'll change state and everything's okay. So eventually device B sends us a request and will acknowledge the receipt of the request. In other words, B extends its hand. So that's step 2. But it's necessary that device A senses B's acknowledgement, and when it does, it will drop its request. In other words, it will change the request from 1 to 0. And hopefully then A will drop its hand, telling device A that device B has actually seen the acknowledgement, and that's important, right? So finally, B's sense A has sensed B's acknowledgement, so B drops its acknowledgement. In other words, it changes its acknowledgement from 1 to 0, and as a result of that, in other words, machine A has seen the acknowledgement, B will turn off its request, drops its hand, lowers its arm, or however you like to describe it. So there are four steps in that. What I'm showing you here are two machines. So there's a machine on the left-hand side, and there's a machine on the right-hand side. And uh, this machine is sending a signal to the other machine. Let me just make sure I've labelled these correctly. So yeah, okay. So let me explain this diagram. This is a state chart, and this is a state in which it's outputting something. In this case, it's a request signal, and request is going to be 1 for as long as this system is in that state. But it's monitoring incoming signals here. This is called a decision box, and we'll see how that operates in a moment. Right. So let's try and explain this diagram. I am sending machine B a signal, request equals 1, and I'm going to continue sending that request signal until machine B, who's monitoring the signal, sees the logic 1 and it'll change state. If it doesn't see it immediately, in other words, the request line is to 0 because it hasn't seen request equals 1, it'll just loop in that state. I mean, it doesn't actually output anything, but it's monitoring, it's making a decision here. Is request 1 or 0? If it's 0, you loop back. If it's 1, you change state and go here. So let's do a little rewind here. And so what I've explained so far is that machine A is going to send out a request for as long as it takes for A to see it. Eventually it will see it, and as a result of that will now output an acknowledgement signal, and it's going to keep sending that signal for as long as let's say for as long as this machine sees the acknowledgement being 1 and will change state. Right. On the other hand, if this machine is faster than machine A, in other words, it changes state very, very quickly, and the request signal as being 1 is still seen here, it's going to wait and continue to output this signal for as long as it takes, until this machine sees the acknowledgement signal to be 1. Eventually, machine A will see the acknowledgement signal as being 1, and it'll change state. And whilst the acknowledgement is 1, it's just going to loop around in this state. So in other words, what I've got here, if you think about it, is that I'm going to send you a signal for as long as it takes for you to see it. And you are going to send me a signal, when appropriate, for as long as it takes for me to see it. And this interaction between two machines, because we're talking about communicating machines, or communicating finite state machines, is appropriate when we're not sure how fast the other machine is and whether or not it's going to be able to see my signal. So you use this signalling scheme in those cases where you don't know anything about the other machine's speed relative to your own speed. And I'm here referring back to my discussion on the synchronization problem. So hopefully, in conjunction with that, you'll fully understand why it's necessary to use this heavyweight 4-cycle full handshake scheme to guarantee communications. And we could take this a little bit further, and suppose that we wish to link serial machines in parallel. I mean, what I want to happen, perhaps, is that we want to operate two machines in parallel in such a way that if A is performing task 1 and B is to perform task 2, in such a way that no matter how long it takes machine A to perform T1 or machine B to perform the other task T2, A and B are both to start at the same time and operate in parallel. So what signalling scheme would guarantee that this is the case? Namely that two machines, A and B, will actually start operation at the same time, and whichever machine finishes is going to wait until the other machine has finished, and then they start all over again in parallel. Um, so here we're thinking about, well, maybe the two machines have got the same clock. So if machine A here sends machine B a signal, it's definitely going to set because they're being clocked at the same time. They've got the same clock. There's no risk that machine B won't see this signal B when it's sent. So let me explain this. So I'm reverting back to just ordinary finite state machine diagrams, in other words, loops and arcs. But I could have expressed this in terms of a state chart. In other words, those little boxes and decision diamonds, if you like. So whilst it's not the case that in other words, A hasn't been seen, I'm going to output B. And this machine, the description of this machine is that whilst signal B is 0, not B, in other words, I'm going to output an A. So if you think about it, let's supposing at the exact same time A changes to 1 and B changes to 1. So what's actually going to happen is that um, I'm actually saying A change to 1. So I've seen A signal, and I'm going to leave this state. And if B changes to 1, it means that, here we go, look, so B changes to 1. It means that it's seen this signal B. B is 1. So both machines will start at exactly the same time by going into these two states. And I represent the task 1 by this state and task 2 by this state. So some of you might say, well, is there any possibility that you can get rid of the handshake? Do you need it? Do you really, really need it? Could you get rid of them? Is there an alternative scheme? And the answer is yes, because I can encode data in such a way that if I want to send a 1, I use two wires. The first wire contains a 0 and the second wire is a 1. If I want to send a 0, I use two wires, and the first wire is 0 and the first wire is logic 1 and the second wire is 0. So it's 0, 1, 1, 0. And the interesting thing is that if I resorted to transmitting data using two wires per bit of information, I can easily test whether or not I've received a valid bit of information, because all I have to do is to make sure that at most one appears on each pair of lines, and I can do that by using a simple logic gate arrangement. So I can test, there's a test for knowing whether or not another system has sent me valid data. And the worst thing that could happen is that I start um, interpreting the data on a data bus and it's not actually valid. It's not what was intended to be for the other system to send to me. So I'll finish at this point with the view that it's quite interesting, and it might want, you might want to explore this a little bit, because I can actually tell when another system has actually finished the work I've given to that system. So I'm not sure about this ringing a bell. It probably doesn't, because you haven't ever seen it before. But it's practical and very interesting use of this idea of a circuit being able to indicate at the end of processing. I mean, you don't need a clock to determine. You don't need a signal to tell the other system whether or not you've got a valid result on your output. The first system can actually tell for itself. So I'll leave it at that point. But having said that, I'm going to try and tell you about one other thing before I do move on. So let me see if I got the yeah, I've got it here. So I'm showing. It's a very short little presentation, and this is something new, and it sort of completes what I've just been talking about. It explains it a little bit more. So there are two topics here, and I want to define what's called the synchronization problem, and the signaling schemes between two autonomous systems is what I've just described. Okay, so just move on a little bit, and you can read this if you want. Right. Like, you can readily imagine a system which, when fed signals, signals, it will respond appropriately. And often the two systems have independent clocks. But the digital universe arranges itself hierarchically, and very often we witness the fact that our controller is often a controlled system, and so on. And to get evidence or examples of this, we can simply open up your PC or your laptop and see that there's an enormous number of controllers and controlled subsystems. So, for example, typically every bus has its own controller. It controls which data is actually going to be transmitted on a particular bus. Or maybe you've got a controller for a system that gathers together incoming datagrams, packets of data from the internet, and so on. And I mean, my argument has always been that a PC itself is nothing other than a finite state machine, and so on. So just move on a little bit, because this isn't absolutely central to what I want to define. So yeah. Today and right now we're going to get to grips with the so-called problem of synchronization, and how, as a system designer, which you may be one day, we can introduce simple circuitry to resolve the problem of synchronization. So I need to explain what the synchronization problem. So the synchronization problem typically arises when a controlled system over which we have no control returns short, narrow pulses. And the question is, how do we actually get to see these narrow pulses? I'm sorry, I'm going all over the place here. How do we get to see the system's short, narrow, perhaps status pulses. It's important that we do see these. I mean, maybe it's a sort of car engine monitoring system that's actually telling another system that the petrol mix is too rich and we need to do something urgently to correct that. How do we get to see these, given that our registers can only capture, so this is important, our registers, our memory cells can only capture data on the rising edge of the system clock. So the problem arises when TP is strictly less than TC, or just rearranging terms, the frequency of C, the frequency of the clock, is greater than the reciprocal of 1 divided by TP. Right. When there's a failure of this relationship, in other words, FC is equal to or less than this sum. So let's have a look at a diagram making this clear. We can think of the system clock as providing a sampling period. Every tick of the clock, we're looking at a data line. And to sample the data, our clock going into a memory cell must have a rising edge. I mean, I think it was last week I showed you a diagram of a positive edge triggered D-type flip-flop. Sounds very complicated, but it's not. And you've got to make sure that the data is settled, is stable at a time setup units before the incoming rising edge. If you do that, then there'll be no system malfunction and you'll be able to memorize the bit on the data line. So here we go. Have a look at this. So this waveform, this logic 1 to logic 0, logic 1 to logic 0, I'm supposing is the system clock. So TC represents the time it takes for one falling edge to the next falling edge to occur. It's the clock period. Okay, TC is the clock period. This is the clock signal. Goes down, goes up, and then goes down. The area I've indicated by these two arrows is the clock period, TC. So the external signal of interest is this here. It goes to logic 1 for a very brief period of time and returns to logic 0. So in other words, it's a short, narrow, active low pulse. It's 0 to 1, 1 to 0. And this is the period, if I can call it that. In other words, it's the distance between a rising edge and a falling edge. And in other words, this pulse lasts exactly TP units of time. And it occurs at this point in time. Here we are, look, this point in time. And notice one thing. Notice that it occurs later than the arrival of this rising edge of the clock. Look, here it occurs at this point in time. And the rising edge of the important rising edge of the clock has occurred well before the arrival of this narrow pulse. Significance of that is that the system whose clock this is a clock belonging to some system, some memory cells, for example, it won't see this narrow pulse. It won't see it 0 to 1. It won't see it. Why? Because it occurs at a time later than the arrival of the rising edge of the clock. And this is what I mean by saying that there is a problem if the frequency of, well, it occurs if TP is strictly less than TC. And here we've actually got a case of TP, which is this distance here, is much less than the clock period, which is this distance here. And as a result, as I've said, I think I've said it twice, this system's memory won't actually register or remember this possibly very, very important incoming pulse, 0 to 1 pulse. And to resolve all this, we've got to make sure that the pulse of an external signal, excuse me, pulse of this external signal, the width of this pulse has got to be greater than the frequency than the period of the clock. Fc, the frequency of the clock, is 1 and divided by t, so we've just got to make sure that the frequency of the clock is greater than 1 divided by Tp. In other words, the number of the widths of the incoming clock pulse dividing the number 1. Right, it's got to be greater than that. I mean, if that is the case, I mean, just if you imagine, look, so here, watch my cursor. I've got TP here. I'm drawing TP here, and I'm going to make sure it's greater than the clock period. So it's going to look like that. And there is no doubt in anybody's mind that when the clock pulse goes from 0 to 1, it will actually see that the pulse is logic 1. Right, because let me just draw this. No, let me draw that. And what I'm talking about, I'm looking at a case where the clock pulse is actually going to be like that. And at this point in time, which indicates the rising edge of the clock period. This is important for the function of the memory cell. A 0 to 1 transition occurs. It will see this pulse as being 1, and it will correctly register that. Okay, so if you're interested, again, I could actually devise, I mean, I'm not intending you to look at this in any great detail, but here's a bit of hardware. I've got a bit of circuitry here that will guarantee that a narrow pulse coming in here will actually be captured on this line here. This will be the Q line will be logic 1 if there's a short pulse coming in here, and it'll stay at 1 until I've actually managed to capture that signal. So I can actually synchronize a sort of almost like a random incoming narrow pulse to a main system clock. I mean, maybe this is part of a lot of hardware to detect an incoming missile, and the fact that I've got a narrow pulse on this coming in is from some radar station, and it indicates the presence of a hostile, possibly hostile incoming missile. I'll get to see it. I'm going to be alerted. Anyway, that's all. So I've got two quite separate subtopics that I'm discussing here. The first is the first part of the video, which is simply missing from the uh, the recording I made of topic 5 last week. And the second part is just to give you a clear idea of what synchronization probably is. You need to understand that in order to be motivated to understand the full handshake. Right, the full handshake occurs when one or the other systems is much faster than the other. So uh, you're going to have a situation probably. There's nothing you can do about it. You just got to accept it. You're going to accept that. Let me see. You've got to accept that you've got to deal with this situation from occurring. Okay, you must avoid the case where you've got a narrow pulse coming in relative to a much larger clock period, and this is the important event taking place, a rising edge of the clock signal. Okay, so thanks very much for listening.